All right, here we are again. So where were we yesterday? Oh, I know. We're almost done with the measures of dispersion. Let me get those notes open again. Let's see. So this is we're getting towards the end of chapter 3, and then we'll later on today we'll start chapter 5. Oops, not that one. And not that one. Hold on one second. Here we go. So let's say the 8th, yes. All right, so you recall from yesterday, I assume you were all here yesterday, that we introduced several new concepts. We introduced some key terms like population versus sample, and we talked about the idea that a sample is a subset of a population. Most of the time we'll be analyzing samples because it takes a long time and is very costly typically to gather up all the elements of a population. So instead, we'll usually resort to samples. The only problem is, of course, with samples is that we have to choose them very carefully. If they don't reflect the underlying population, then our results will not be very useful. So we went ahead and we introduced some measures of central tendency, and we looked at 3 of them, the mean, the median, and the mode, and we calculated them, we analyzed their properties, and we saw that each one can be calculated separately for populations and samples, but the actual calculations are the same in all 3 cases. We also looked at, well, of course, we learned more about the summation operator, which we'll be seeing again and again in this class. What else did we do? Oh, we introduced weighted averages, which are used for cases where we have repeated elements in our sample or population. We looked at the case of the lottery, and of course, the one that interested everyone was the GPA. Now you know how they calculate those numbers, by the way. If you ever wondered where they got those numbers, this is what they're actually doing. Let's see, what else did we do? We explained why you would use the median when a sample or population has outliers instead of the mean, because the mean is distorted by the existence of outliers, whereas the median is not. Let's see, what else did we do? Histograms, yes, a very important graphical device that we'll see quite frequently throughout this course because it's an extremely useful way of summarizing the information found in either a sample or a population. We looked at the relationship between the mean, median, and mode. We saw that there's 3 basic cases we might encounter: data that are negatively skewed, where the mean is less than the median, which is less than the mode. And the picture, you can see in this case, when we're describing stock returns, you can see that the losses by far outweigh the gains. So this data set is said to be negatively skewed. And you can tell without the graph because if you were to calculate the mean, median, and mode, you'd see that they have this particular relationship between them. Symmetry means that everything's equal. They're all 3 of them are the same. And all 3 of them are the same. And therefore, there's a balance between, in the case of stock returns, gains and losses. Okay, so in other words, if you look at this picture, you'll see that I drew this line down the middle. The area to the left is an exact mirror image of the area to the right. And then the last case that we looked at was positively skewed data, where the mean is now the largest, which is in turn greater than the median, and then the mode. And when you look at this graph, this is the one that we all are hoping for when we buy stocks, because you can see the gains outweigh the losses. Okay, and that's what we're hoping for with stocks. Okay, then we introduce measures of dispersion, which are essentially trying to show us how spread out the data are from the center. And these are very useful for many different types of applications. In particular, if you're looking at stocks again, measures of dispersion can be thought of as measures of risk. So when you buy stocks, of course, there's a lot of risk involved. And so the more spread out the returns are, the riskier the stock will be. So I showed you a couple of quick graphs. The stock on the left is safer than the one on the right, simply because in the first case, the returns are very close to each other. You don't tend to get any years with very small outcomes or very bad outcomes, but you also don't have any years where you have an extremely large return either. Whereas the one on the right, anything can happen, anything from a huge loss to a huge gain and everything in between. So the stock on the right would be considered to be a riskier stock than the one on the left. And you can see the histogram helps us easily understand this relationship. All right, we can look at the numbers too, but having a graph is often very helpful. And then we mentioned that several of the most important measures of dispersion, which we got through all of them, but the last one. Remember, the range is simply the difference between the largest and the smallest values. The quantiles break the data up into four sections, each of which contains 25% of the data. The variance and standard deviation are actually related to each other because the standard deviation is simply the square root of the variance. And the reason why we often prefer the standard deviation is because of the units. Okay, the standard deviation has the same units as the underlying data. The variance is measured in squared units, and that's a real problem. So the standard deviation itself is simply the square root of the variance. So that leaves us with one more measure. Now, this measure is actually related to ones we've already seen. It's not completely new, but it is different in an important way. So let's jump ahead and take a look at this coefficient of variation. Okay, here it is. This tells me how spread out the members of the sample or population are relative to the mean. So in other words, it's not just telling me how spread out the data are, but how spread are they compared to the mean. And so you'll see what we mean in a couple of minutes when we look at this example. But sometimes it's thought of as a measure of relative dispersion. In fact, why don't I add that right here? The coefficient of variation is often referred to as a measure of relative dispersion, because it is being measured compared to the mean. It isn't an absolute measure like the other ones. And for certain applications, it is extremely helpful. Now, how does it work? This one is the same for both samples and populations, the calculations at least. What you're doing is you're taking the ratio of the standard deviation to the mean, and then you multiply that by 100 to convert it into a percent. Okay. Now, what that means, in fact, you know what, let me put this in here just to make sure it's very clear. That means for a sample, the coefficient of variation would be S over X bar times 100. And for a population, it's going to be, based on the Greek letters, sigma over mu times 100. But you can see it's the same thing. All right, so it's easy to calculate, and it's based on measures we've already calculated. Like I said, it's not completely new. It's just a different way of looking at dispersion. So imagine the following situation. We have two portfolios of stocks. We'll just call them A and B, and we'll treat each one as a separate population. Okay. And so we're told two things. For each portfolio, we're told the mean and the standard deviation. So for example, in portfolio A, this is the mean rate of return, by the way. If you notice, by the way, this is an important detail. Even though it says 8%, I've converted that into a decimal. I personally find that it's easier to work with decimals than to write these as percentages. So whenever we run across an example like this, I'm going to always convert it to a decimal. You can always convert it back later on when you're done. but I do find that the math is simpler if you're using decimals rather than percentages. Down here, we have the standard deviation or risk. I'll write that as the risk of the stock because that's what it is. It tells me how much uncertainty there is associated with this 8% rate of return. Now, by the way, here's an interesting side note. If the mean was, if the stock return was always 8%, the standard deviation would be 0, meaning that it's always the same. But that's clearly not the case here, is it? No. In fact, it can change quite a bit from one year to the next. So the standard deviation reflects how far away from that 8% the mean can, the returns can actually be. Now, what about portfolio B? Well, we're going to see with portfolio B that both numbers are higher. All right, so here we have 10 and 30%. Now, if you notice, let me just write this over here so you can see it again. What typically happens with financial securities like stocks is that normally a stock with a higher standard deviation or risk has a higher average return. That's pretty standard. Most of the time in the marketplace, you'll see that the higher the risk of the stock, in general, the higher should be the rate of return. Okay, so in other words, if you want to really make a lot of money in the stock market, you really have to take on a significant amount of risk because otherwise it just isn't going to happen. So you can see that between the two of these, A is a little safer, but it also only has an 8% rate of return than B, which is at 10%. Now, the question is, which one do you pick? That could depend on a lot of factors, like how much risk you're willing to tolerate. But the coefficient of variation can give us a very useful piece of insight into how to make this decision. So let's do that. Let's calculate the coefficient of variation for the two portfolios. Now remember, it's simply the standard deviation over the mean times 100. So for A, that translates into 200%, which basically means there's twice as much risk as return with the stock. Okay, now is that a lot? It's hard to say. We have to now do the same thing for B and see what kind of result we get. And when we have that information, that will help us decide which portfolio we should buy. All right. So for B, look at that, it's 300%. There is 3 times as much return, or I should say the return is 3 times the risk. Now, between the two of them then, you notice if we want to summarize these, A, coefficient of variation is 200%. For B, it's 300%. So because this measure represents the risk to return. Oh, you know what I just realized? Oops. I'm sorry. I wrote this backwards, didn't I? Yes. Sorry. I just noticed it now. There's twice as, sorry, I screwed it up royally here. There's twice as much risk as return. I just got it backwards. Sorry. It's twice as much risk because risk is in the numerator and the mean is the return. So I got it backwards. Sorry about that. There's twice as much risk as return here. And for this one, of course, that means the risk is 3 times the return. So therefore, which one of these would you want? That tells me that A is probably the better choice, because the level of risk to return is only 2 to 1 instead of 3 to 1. So in a measure like this, a lower coefficient of variation is better. So at least with stocks, a lower coefficient of variation is better. And so you can see it would be difficult to judge this with just the mean and standard deviation. Here, it means you can compare them all on an equal footing, and that's really why we like this measure. All right, now already we've seen 2 types of measures: the measures of central tendency, which help us find the center of our data, and the measures of dispersion, which help us understand how spread out the returns are, or whatever the values happen to be. It's not always returns. It could be anything. It could be temperatures, it could be heights, it could be weights. But the point of it is that the measures of dispersion explain to us how spread out the values are relative to the center. So the third and final set of measures that we want to consider are designed to help us understand the relationship between 2 different samples or populations. Okay, and so these types of measures are known as measures of association. And it is very possible that you've heard these words before, especially correlation. So we're going to take a little detour here now and discuss in general what these terms are actually meant to represent. Okay, we have covariance and correlation, and what they're trying to do is capture the extent to which 2 variables move in the same direction. So what do we mean by that? Well, all right, let's think about this case. Suppose that we are studying the relationship between a corporation's sales and its profits. In most years, if sales rise, profits rise, and vice versa. Because obviously the higher your sales are, most likely your profits will go up. It isn't always the same amount, and it isn't always true. But most of the time, when sales go up, profits will go up as well. So the association between these variables is positive. Okay, there's a positive association between the variables. There's a tendency for them to move in the same direction. When one goes up, the other goes up, and vice versa. Now, in order to properly analyze this type of setup, we need a special kind of graph, which, in fact, you know what we could do here? Just in case, this might be fun for you to see. Actually, I think I may have already done this. Let me go look at my, here we go, my folder here. I do already have one. What I've done here is created some, oh, this is nice. Okay, I'll post these later on, by the way, onto Moodle. I've done exactly what I described here. I've got a corporation. Now, I've made these numbers up, of course. And the sales are in the first column, or second column, actually, and then the profits are in the third column. And they're in millions of dollars. And you can see that during good years for the sales, there's a tendency for the profits to be high as well, and vice versa. What you're seeing here is this graphical device known as a scatter plot. Each of these points is a single year taken from this table. So for example, this one, it looks like that would be this year right here, year 4, where the profits are 19 million and the sales are about 85. Way up here, what do we have here? It looks like that would be this last year, where profits are 44 million and the sales are 150. So each one of these points represents one of these years. And if you notice, if you look at the points, there's a tendency for them to move up towards the upper right-hand corner, which means they're both rising or falling at the same time. And in fact, if you recall from high school math, if you look at this plot, you can see that up in upper right-hand corner is the so-called first quadrant. Over to the left is the second quadrant, down here is the third quadrant, and down in the bottom right is the fourth quadrant. And almost all the points are either in the first or the third quadrant. And that means that we have a positive relationship between these variables. All right, and that just simply means that the two of them tend to move in the same direction. Now, is there another possible relationship between two variables? Of course. What about this case? What if I'm looking at not sales and profits, but costs of production and profits? If my costs of production go up, my profits will tend to fall and vice versa. So I plotted these out in the same setup in the scatter plot. And if you notice this time, the points are moving down towards the right. In fact, most of the points are in either the second or the fourth quadrant. And what this tells me is that the variables are negatively related, which simply means when one goes up, the other has a tendency to go down and vice versa. Wow. Okay. Now there's a third possibility here, and that's the case when the two variables are simply not related to each other, like temperature and profits. Well, you can see the points are sort of randomly scattered throughout all four quadrants. This line, that's an attempt to connect the points, is almost perfectly flat. In other words, the slope is just about 0. So here we would say that the variables are unrelated to each other, or possibly we could call them independent. So remember, the positively related case looks like this. Negatively related looks like this. Unrelated or independent looks like this. Those are 3 extreme cases. Most cases fall somewhere in between. So the question is, now you notice I've already calculated in Excel the covariance and the correlation. What we have to do now is understand how these numbers are calculated and what do they mean. Okay, and if you notice, here they're both positive because we have the positive relationship. Here they're both negative because of the negative relationship. Here they're close to 0, although it's hard to tell right here, but they are close to 0. Okay. I don't think, well, we do need this if you want to look at the Excel formulas. You can do this at home. You can look at the Excel formulas. If you know Excel at all, you know that they have lots of formulas in here, and you can use them to come up with these measures, but we're going to use the actual formulas here. All right, now the covariance comes first. If the covariance is positive, X and Y tend to increase or decrease at the same time, as we've just seen. If it's negative, they tend to go in opposite directions. And if covariance is 0 or very close to it, then the two variables are unrelated to each other. All right, so let's jump ahead here a little bit. Now, this is the formula for the sample covariance. Now here, there's a separate formula for the sample version and the population version. There's just a couple of things that are different here. First of all, there are two samples instead of one. And in the first case, the sample elements are x's, and in the second case, they're y's. And then in sample y, of course, this y bar is the mean of all the y's. It's no different than x bar, which is, of course, the sum of the x's over n. This is the sample size. Now, one thing I do want to point out is that both samples have n elements in them. They can't be different, otherwise we cannot calculate this measure. One last thing. Yesterday, we saw that S is being used to represent the sample standard deviation. By putting in these two subscripts, we now are using this to represent the sample covariance. And the subscripts are there to remind you that it's the covariance and not the standard deviation. All right, so we're going to do this by hand once. And you'll see it's a bit of a, it's a complicated process, but it's not as bad maybe as it looks. Okay, let's look at the data. So here's our two samples. We have 5 elements in each one. And the first thing we want to do is calculate their means. All right, I'll give you a minute to catch up. Okay, so let's calculate x bar, and you can see you're just adding up the elements of x and dividing by 5, so that gives me 1. Yes, so you're just adding them up. You don't have to sort them or anything. Just add them up and divide by 5. And you'll have a sample mean for x of 1. And then we do the same thing for y. We want to calculate y bar as well. So let's see what that turns out to be. Add them up, divide by 5, and you have 15/5 or 3. Now, of course, we need that information because that's a major part of the formula. The two means now here, they're both integers, which makes things a little easier. Okay, now let me just go back and copy for you this formula so you can keep an eye on what's going on here. So what you're actually doing here is that you're going through the list. I don't think there's enough room, well, maybe there is, to copy the data back again. Hold on. Oh, oh boy. No, maybe we can do this. Just to keep it all together in one place. All right, I think we may have succeeded. Uh, I know what I'll do. I'll make the font smaller. There we go. That's perfect. Same thing over here. I'll make the font a little smaller. All right, so what exactly is going on here? You're going through the list. Now, so in other words, this is X1 and this is X bar. This is Y1 minus Y bar. This is X2 minus X bar times Y2 minus Y bar. And then you work your way through the whole thing. This last one, for example, is X5 minus X bar times Y5 minus Y bar. In each case, we multiply them together, we add them up. At the end, we divide by, if you notice, not 5, but 4. And it turns out that the covariance in this example is -1. And because it's negative, that means that the two variables show a tendency to move in opposite directions. Negative means opposite directions. Okay, that's what negative means. Okay, now the problem, oh, by the way, I'll just quickly show you what the equivalent formula is for the population covariance, and then I'll start to tell you what are some of the drawbacks to the covariance measure. So as you can probably imagine, the population covariance formula is similar to the sample version, except we changed into Greek letters. The lowercase n becomes capital N, but there's also one more difference. All right, what could it be? Okay, so now the capital N's I mentioned, the Greek letters, this is the mean of X. This is the mean of Y. And if you notice, these are the Greek letter mu. Remember yesterday, we used this as a population mean. Because there's two populations now, we need some way to tell them apart. So we're going to have this subscript here that we did not have yesterday. Okay, so when there's two or more population means involved, we do need to keep track of them somehow, and that's done with a subscript. Now over here on the left, you'll notice yesterday we used the sigma as the population standard deviation. So what gives? How can we use the same symbol twice? Well, we're not really, because here we have the two subscripts. And that's our signal that this whole thing is the population covariance. Between X and Y. Okay. So you can see though, and remember with the variance, we had a different value in the denominator. The same thing happened here. We're actually dividing by n instead of n minus 1, just like with the variance. Yeah, there's very, very little room here, but no, there we go. We fit it in. Okay, so remember, this is just like the relationship between the sample variance and the population variance. You do divide by a different number here. This is for the sample, this is for the population. Okay. Now that we've done this, what we'd like to do is start to understand. Now, remember yesterday we said that the variance is important, but it's not as useful as the standard deviation because of the units. Well, it turns out that the population covariance and the standard sample covariance have issues as well that we have to address. And it'll turn out that there's another alternative measure that is actually more useful. But before we do that, we just want to take a look at this example again. If you notice, the covariance is -1. We know that the variables tend to move in opposite directions. What we don't know is how strong is this effect. Now, what do I mean by that? All right, well, let me show you a couple of graphs that both are possibilities in this case. We could have a scatter plot. Now, remember, this is a negative value. The points are moving down towards the right. In other words, they tend to stay in the second and fourth quadrants. And so let's draw the trend line here. Okay, they look very similar to each other, but let's see what's different. On the left, the points are really, really close to that line. And on the right, they're not very close at all. So in the first case, we have a strong negative relationship. In the second case, we have a weak negative relationship. The question is, which one do we have with our case? The answer is you can't tell. All we know is that the covariance is negative. We can't be sure whether it's a strong negative relationship or a strong weak negative relationship. So the covariance doesn't really give us any useful information about the strength of that relationship. So that's one reason why we normally prefer to use the correlation instead of the covariance. So in other words, let's look at this now. The correlation is closely related to the covariance, but it has one huge advantage. It can only range between negative and +1, making it easier to interpret than the covariance. The covariance has no upper or lower limits. But the correlation does. Okay, so in other words, that's a huge advantage. Now, in fact, so much so, let me show you some graphs so you can see what this is all about. For this, I'm actually going to need, well, 2 is probably good enough. Okay. So let's say that we had that scenario from before. Oops. Now, with the covariance, we couldn't really tell these two apart, but here, for example, the correlation is going to be very close to -1. Let's say that it's -0.9. And over here, the correlation is -0.2. So remember, the correlation cannot fall outside the range, positive to -1. So that means that this first one is a strong negative relationship. This one is a weak negative relationship. And with the covariance, you could not tell without the graph which is which. Here, though, because we know what the upper and lower limits are for correlation, you can tell just from the correlation coefficient, not only the direction of this relationship, but its strength. And that's a huge deal. Makes all the difference in the world with interpreting our results. And we can say the same thing about positive relationships. Remember, there's an upper limit as well. That upper limit is 1. So therefore, let's take a look at a couple of new graphs and see what would happen with positive relationships. All right. Let's see. So this time, the points are moving in sort of a northeasterly direction. Something like that. That's good enough. All right, so the one on the left is clearly a strong positive correlation or strong positive relationship. And this one obviously is a strong, weak positive relationship. And the correlation is, let's say this one, and again, I'm making these numbers up, but this one could be, for example, positive 0.8. And this one could be 0.1. And all that means is that they're both positive, but the one on the left is much stronger than the one on the right. And so again, we can tell just by looking at the correlation how strong this relationship is. We could not do that with a covariance. Now, there's a third possibility too. The two variables could be have essentially no relationship between them at all. That's when the correlation gets to be very, very close to 0. It may not be exactly 0, but it will be close. Okay, so let's say we have something like this. that would mean the correlation is zero. No relationship. Or we could say that X and Y are independent. Okay, so you can see that the correlation can give us a lot of useful information about both the strength and the direction of these relationships. Another advantage is this. Another advantage of the correlation over the covariance is that the covariance is affected by the units in which it is measured. So for example, the correlation will provide a different value. Sorry, the covariance would be different if the data is measured in inches versus millimeters. This is not true for the correlation. It is said to be unit free. Okay, so that's another reason. So those two reasons are enough for us to recognize that the correlation is the better approach, but we need the covariance to get to the correlation, just like we needed to calculate the variance to come up with our standard deviation. So, and you'll see why in a second when I'll show you the formula. The sample correlation coefficient is first, and you'll see it's pretty straightforward. And so here's what it looks like. Now you recognize some of these symbols already. This is the sample covariance. Now this is the samples, this is the standard deviation of sample X. And this is the standard deviation of sample Y. And again, you notice because there's two different samples here, we need subscripts to tell us which is which. We didn't have this before. Now over here on the left, this R with the XY, this is we call this the sample correlation coefficient. R with a subscript of X and Y. The two subscripts reminds us that in this case, at least, this is the correlation because it's a relationship between two samples, not just one. So basically, once you know the sample covariance, you now simply divide by the two standard deviations and you'll have your sample correlation. And again, because of the way it's calculated, this measure is always between positive and -1. And that's one of the nice things about it. All right. So now what we're going to do here is go back and revisit that last example we had. We had the two samples and we went through all the steps to discover that the sample covariance was -1. And we recognize, well, yes, that's certainly a negative relationship, but we don't know how strong. So now's our chance to find out how strong this relationship is. So we have to, unfortunately, though, go through two more steps. We have to calculate both the sample standard deviation for X and for Y. like we did yesterday. So I've already gone through all the steps for you here. You'll recognize this from yesterday. What are we actually doing here? You go through all the x's, and in each case, you're subtracting the mean of 1. You square them, add them up, divide by, in this case, 4. Okay, remember, n is the sample size. And when you're done, you'll have approximately 2.1213. All right, so if you want to practice with that one right now, I'll give you a couple of minutes to just take out the old calculator and make sure you can reproduce this number before we go any further. So we'll stop for a minute and make sure that you can actually get the same number. All right, so we need the practice. And just to be helpful, what you should probably do, like I said yesterday, is first evaluate what's going on inside the parentheses before you do the squaring. Okay, well, anyway, oh boy, so I have no space at all here. Okay, so you basically got the square root of 18/4. And if you take out your calculator, 2.1213, yes, perfect. All right, now of course you have to go through the same steps for the y. If you recall, the y bar is 3. Okay, so same thing. Now remember, y bar is 3, so we're going to go through all the y's, have 3 subtracted from them before they're squared. And I'll move that way up here on the top. Of 0 plus 1 plus 1 plus 9 plus 9 over 4. So that's 24th, which is 5. And radical 5 is approximately 2.2361. Perfect. Whoops. So you've got your 2 standard deviations, you've got your covariance. Now we're ready to get our correlation coefficient and find out just how strong our relationship really is. All right, here we go. So you plug everything in and you end up with approximately negative 0.2108. Now that, remember, is one of the relatively weak ones because that's getting fairly close to 0. It's negative, but not very strong. Okay, so there's not a very powerful relationship here, but at least we know that it's negative. Now, knowing that is a lot better than knowing just the covariance is -1, because that didn't tell us anything about the strength of this relationship, just the direction. Okay. All right. Now, there's only one more thing to look at here, and that is the equivalent formula for the population. Okay, now here, just like with all the other cases, there's an equivalent version back and forth between the samples and the populations. And the notation is different here, as you'll see, but the formula is exactly the same. All right, so here we go. Let's see what's going on here. So you recognize all of these. This is the population covariance. This is the standard deviation of population X. And this is the standard deviation of population Y. And now this is a new Greek letter, which we haven't seen before. This is the Greek letter rho, and it represents the population correlation coefficient. So, of course, you can see that the formula is exactly the same, except for all the Greek letters. These two are calculated in exactly the same way. All right. Well, you know what? We plowed through that chapter fairly quickly, but of course, it is the summer, and that's what we have to do. So don't forget, what I want you to do for Monday is do the chapter 3 problem set just to make sure you get some practice. And we'll go over it, but you should hand it in on Monday. And it's just exactly what we're doing here. So the only way to make sure you understand what we've been doing is to try it yourself. You can watch it all day long if you want, but until you put your pen on that paper and start doing it yourself, you won't know if you truly understand it or not. If you don't, it will only take a few tries to get it, I think. So in other words, if you're making a mistake, we'll figure out what's going on. And once you got the hang of it, you should never make a mistake again, unless you're getting careless, of course. So I think this is a great class for homeworks because it's a kind of class where you can learn by practicing. All right, now once that's done, now this is it. We're completely finished with this chapter, so we're ready to start the next chapter, which is not 4, but 5. Okay, we had to make some budget cuts. We're going to go directly to 5. And 5 is a very different chapter. You'll see what I mean in a few minutes. Oh, you know what I forgot to do? Let's go back to this example and look at our results. Look at this one. This is the one we had earlier. The correlation is 0.93. And it makes sense because you can see how close these points are to the that line, which is called a trend line. The relationship is almost perfect. That's how close these points are to the line. This one, the relationship is a little bit weaker, but it's still very strong. Negative 0.906. That's still a very strong negative relationship. The points are very, very close to that line. This one, not so much. The points are pretty much scattered all over the place. The correlation is very slightly negative because it's a very weak relationship. It's negative, but it's very, very weak. It's actually very close to 0. All right, so that's enough of that. Now it's time for chapter 5. Okay, so with chapter 5, we're moving into a bit of a different direction. We're going to be considering an area of mathematics called probability theory. Why are we doing this? Because all statistics is ultimately based on probability theory, which in turn is based on set theory. So we're going to see a lot of both in this chapter. We're going to introduce a lot of very important fundamental concepts that we'll need throughout the course. So here, the questions are not so time consuming, the problems, the calculations, I mean, but everything is a little bit more theoretical and conceptual. All right, so we have to introduce some very important terminology as well. So we're going to start out by noting that probability theory ultimately is designed to provide us with a mathematical framework for measuring uncertainty. It is ultimately based on the concept of the random experiment, which we'll define in a minute. So we're trying to find a way to assign numbers to how uncertain an event is actually going to be. In other words, if I want to know the likelihood that the Dow Jones will go up next week, I'd like to have some way of assigning a probability to that. Or if I want to know the likelihood that the weather will improve this summer, or anything can be, we can have probabilities attached to it. Now, a random experiment is a process, and there's many different types that we can define. What matters is that we have outcomes that are generated in such a way that we know all the possible outcomes in advance, but not the actual outcomes. So, it's still a very general concept. Let me show you a few simple examples of this. Now, by the way, it turns out that games of chance lend themselves very nicely to examples in this area. So we'll be doing some of that. For example, rolling dice and picking cards from a deck, spinning a roulette wheel, that kind of thing. Well, there you go, a roulette wheel. Now, you've probably seen one of these things, at least on TV. You're not actually allowed to go into a casino in the United States until you're 21. Oops. Although in Canada, depending on what part of Canada you're in, you can get in there as little as, I think, 18, certainly 19 in Ontario. But you may have seen this game like in a James Bond movie. What's going on with this thing? Well, you see there's a ball spinning around in here, and there's a bunch of numbers. And each number is equally likely to turn up when you spin the wheel. And whatever number turns up determines how much money you win when you play this game. So what's interesting about this game is that there are numbers range from 1 to 36, and those numbers are all red or black. And 0 and 00, which are green. Now, each one of these is equally likely to occur. So when we spin the wheel, we know in advance what possibilities there are. There's 38 different numbers that could turn up. Of course, we don't know which one will turn up. And since each number is equally likely, it's easy to calculate probabilities. For example, the probability of getting a 0 is 1 out of 38 because there's 38 wheels. The wheel has 38 numbers, all of which are equally likely. Choosing a card from a deck. Now, a deck of cards has 52 cards, not including the jokers. The probability of picking any one of them is 1 out of 52. So if I wanted to know the probability of picking the 7 of hearts, that would just be 1 out of 52. It's easy. Do I know which card I will pick? Of course not, but I know what is possible. And then rolling a pair of dice, which you've all done during your lifetimes. With a pair of dice, the range of possibilities is from 2 through 12. And there's 36 possible ways this can happen. So we know in advance what could happen. We just don't know what will happen. All right. So these are all examples of a random process. Now, it could be something else. It doesn't have to be a game of chance. Let's say you're managing a bank and you look at your security camera and you want to know during the day how many people use your ATM in the lobby. Because, you're thinking about maybe getting another one if there's customers standing in line all day. So you look at the security tape and you see that, oh, today we had 8 people. The next day you see there's 9. And then so you can use this information to determine the probability that somebody will be using your ATM during a given day. Okay. So now here's a case that we're going to use throughout the chapter. We're going to roll a die twice, but to keep it simple, we're going to assume that we're only paying attention to whether the dice are even or odd. By the way, in case you never noticed this, dice is a plural word. It's the plural of die. Whoops. So it's correct to say a single die. But when you have 2 or more, they're called dice. Okay. Just thought I would mention that. So we have a die that's rolled twice. Each time it turns up either odd or even. Fine. Let's say we're playing some game where we win a prize based on whether or not or the number of odds and evens that turn up. The numbers don't matter. What matters is evens and odds. So each time we do this, we refer to that as a trial of the experiment, because this is an experiment. We're rolling the die twice. We're seeing what happens. We know in advance what might happen. We do not know what will happen. So then only 4 things can happen. Again, we're only keeping track of evens and odds. We get an even on the first roll and another even on the second roll. Or even followed by odd, odd followed by even, odd followed by odd. That's it. And because getting an even or an odd is equally likely, each of these outcomes is equally likely. And so also, just to save time when we write this stuff, we're going to write this first one as simply EE. This will be written as EO. Here we have OE. And here we have OO. And the fact that we're using these braces, that means each one of these are all sets. All right, probability theory, as I said earlier, is based on sets. So that's why it's important to understand set algebra, which we'll review as we go along. So each of these is a set. It contains the outcomes of interest. Now, by the way, if you wanted to do this more, let's say, systematically, you could actually write down a list of all the different ways in which you can roll 2 dice and pick out all the cases where you have even followed by even followed by odd, et cetera, et cetera. What you would discover is that there are 36 total outcomes when you roll 2 dice. And in 9 cases, you get EE. 9 cases, you would have EO. In 9 cases, you would get OE. And in 9 cases, you would get OO. So that means each one of these is equally likely. Specifically, the probability is 9 out of 36, which is 1/4. Okay, now we're going to gather all of these outcomes into a big, gigantic set, which we'll call the sample space. And so for every experiment, there's a sample space. This one happens to have a very simple one. We've got 4 possibilities, each of which is equally likely, and it's written as S for sample space. All probabilities are calculated based on the sample space. All right, well, you'll see what I mean when we get to those examples. All right, so let's see, what's coming up next is starting to get a little bit more involved. So I'll tell you what, just like yesterday, this is probably as good a time as any to have our morning break. So we'll stop for a bit and recover a little. And when we get back, we'll dive more deeply into probability theory. All right. So we'll see you all in a bit. Make sure you get some refreshments. All right, let's do this. All right, so anyway, yes, here's our sample space. So now we're going to define, and we mentioned yesterday, if you recall, what a subset is. Remember, a subset is simply a set contained within another set. So a formal definition here that will be very important is the event, which is itself simply a subset of the entire sample space. So based on the sample space we defined a few minutes ago, suppose we're interested, suppose there's some reason why it matters to us, whether or not there's a maximum of one even number that turns up when we roll the two dice. Okay, so now it's defined here in terms of English. At most, one even number turns up. Now, you can translate that into math by just saying that the number of evens is less than or equal to 1. Or you could simply note that that means OO, because there are no evens, OE, because there's one even, and EO, because there's one even. The only thing you're actually leaving out is the case of two evens. And so this is an event, because it should be pretty clear that F is a subset of S. Okay, remember S equals EE, EO, OE, and OO. And F represents these three elements. Now, this is an event. Now, the reason why this is important is because we now would like to calculate the probability of this event actually happening. Okay, so now here's where we get a bit of a break. The fact that the sample space contains 4 equally likely elements means that the probability of each of these elements is 1/4. Okay, remember, because of the way this was defined, each of these outcomes in the sample space is equally likely to occur. And with 4 of them, that means each one must have a probability of 1/4. So therefore, it stands to reason that the probability of event F could be rewritten as the probability of getting EO plus the probability of getting OE plus the probability of getting OO, which is 1/4 plus 1/4 plus 1/4 or 3/4, or you could write it as 0.75. So that made things a lot easier for us. And in fact, because all these outcomes are equally likely, there's an even quicker way we can do this, but it only works when all the elements are equally likely. What I just did there is always true, even when they're not equally likely. But in the event that they are equally likely, there's a second approach we can take, which is just a little bit quicker. And of course, things, the faster you can do something, the better. So what we're going to do is for any event E where the outcomes are equally likely, we'll show that we can calculate the probability of E by counting the number of elements in E and dividing by the number of elements in the sample space. Okay, so here, in the case of F, we would have counted 3 elements in F. Remember, F is everything except 2 evens. And the entire sample space is all the elements. By the way, I just want to remind everyone with a set, the order in which you write these elements does not actually make any difference. In other words, sometimes before I wrote S with EE first, it doesn't matter. The order is irrelevant. What matters is what elements are actually in this set. So you can see there's 3 elements in F out of a total of 4 in the sample space. That's all we need to determine that the probability of F is 3 out of 4. Okay. Now, before we go any further, we're going to introduce some very important results. These are the so-called axioms of probability. Now, an axiom is basically an assumption on which a system of logic is based. In other words, these are statements that are accepted without proof. We assume that these are true. You've seen some of these probably in high school geometry. But here, these are some statements that we'll accept without proof, and they will form the foundation of all of probability theory. So at least the first 2, I think you'll find to be very straightforward and self-explanatory. The third one is a little bit trickier. All right, so axioms. So any system of logic is based on axioms. So this is no different. So first of all, the probability of any event is non-negative, meaning it can't be negative. We're basically saying right up front, it's not possible for a probability to be negative. Now, the second axiom is that the probability of the entire sample space is 1. And when you combine both of these, that implies, these two together imply that any probability you can think of will always be somewhere between 0 and 1. And furthermore, if an event has a probability of 1, means we have a certain event, something that is guaranteed to be true. A probability of 0 at the other extreme means an impossible event. And then we have everything in between. Okay, so in other words, all probabilities will be somewhere between 0 and 1. If it's exactly 1, that means the event is certain to take place. If it's 0, that means it's not possible for that event to take place. Now, the third axiom is a little bit more complicated. You'll see later on why it's so important. All right, so here we go. If you have any set of events, now here are the key detail. The word disjoint or non-overlapping means the events have no elements in common. Now, down here, you'll see some symbols. You might have forgotten what they mean. This is the symbol for union. And the union means you're taking 2 sets. Let's say you have set A is 1 and 2. And set B is 2 and 3. The union tells us to combine these into a new set that contains all the elements that are either an A or B or possibly both. And so you notice how, even though there was a 2 in both of them, I didn't list it twice. We only want to list the unique elements. So the new set A union B is 1, 2, 3. It is simply the result of taking A and B and combining them. Sometimes, by the way, in some textbooks, union can be written as or, because it means the same thing as the English word or. You may have seen that in whatever book you used in high school. It's possible you saw it listed as or, but formally this is known as U for union. And so here, what's going on? We're combining a large number of disjoint events. The probability of that union can be obtained by simply adding up the probabilities of the individual events. That's what this is telling us. So that's the third and final axiom, but this doesn't work unless the events rather, have no elements in common. So this one doesn't seem to be quite so important, does it? But yes, it turns out to be very important, and we'll run into this later on. The first two are really just there to establish the upper and lower bounds for a probability. This one is a little bit different. And with these in place, every result that we see in probability theory can be derived with these in mind. Okay. Now, with this information in place, we can set up a series of rules of probability. Now, these rules are being applied to typically 2 or more events at the same time. So these are more complicated situations than what we've seen up to this point. You can see the names are the addition rule, the complement rule, and the multiplication rule. So we're going to do these in this order. The first 2 are pretty straightforward. The third one, well, that's going to take a while. Okay. So we'll start at the beginning. Now, before we do this, you know what, I'll tell you what, let's do this. Let's take a bit of a detour and do a quick review of set algebra. We've already done some of this, but I think we could use some more. So union, we've already seen. Let's just say that we have events A, 1, 2, and 3, B, 2, 3, and 4, C will be 5, how about D can be 1 and 2. So for the union, like I said before, I'm literally just combining 2 sets. Okay, or let's say C union D is 1, 2, 5. Now, we also have this other concept or this other operator called intersection. And this is essentially an upside down U. The intersection between A and B is the 2 elements they have in common, 2 and 3. Not all sets have an intersection. A intersects C is, well, there's no elements in common. This is said to be the empty set. Okay, so there doesn't have to be an element in common between them. And that means that A and C are, as we saw earlier, disjoint. Or mutually, sometimes they're called mutually exclusive. Okay, and now we have already seen the concept of subset. For example, D is a subset of A because every element in D rather, is an element of A. On the other hand, D is not a subset of B, which we write with a slash through it. Not every element of D is an element of B. And so we say that D is not a subset of B. D is a subset of A, but not of B. Okay, so that should take care of us so far. I mean, there's more, but for the time being, that'll be our quickie review of set theory, or set algebra, I should say. Okay. So we're going to start by defining the addition rule. And the addition rule, it tells us what to do in the case that we have the union of two different events. And you can see it's pretty straightforward. So the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. Now here, if you notice, we did not assume that A and B are disjoint. This applies to all events. Okay, let's do an example. So let's see. Suppose we go back to our original case of the die rolling experiment. So recall the sample space is EE, EO, OE, and OO. We're going to define the event A to be the first roll is even, which means that's EE and EO. B exactly one roll is odd, that would be EO and OE. Okay, so often in these cases, what you need to do is identify what elements belong to that event before you start trying to calculate probabilities. Now, what do we want to know here? What's the probability of getting either the first roll is even, which is A, or exactly one roll is odd? So in other words, what you're being asked for is the probability of A union B. The word or means union. Okay, so remember that. Or is union and is associated with intersection. Now, luckily, we've already been introduced to this addition rule, so we know what to do. But if you notice, it requires us to know the probabilities of A, B, and their intersection. So here's what we'll do. So here's A, here's B, here's the intersection between them. Now, remember, this is a sample space where all the elements are equally likely. So the probability of A can be counted as 2 out of 4. There's 2 elements in A. I'll write that up here. Because the elements in the sample space are equally likely. So the probability of A is simply 2/4. The probability of B is 2/4 again. And the probability of A intersect B is therefore 1/4. So now all we have to do is plug all these numbers into the rule. Okay, let me give you a minute to catch up. All right, here we go. So you plug in the numbers and voila, 3/4, that's our probability. No problem. It was easy. Now, here's something else we could have done, though. There's almost always, more than one way of accomplishing anything in math and statistics. All right, so what other approach could we have taken? Well, again, based on the idea that all the elements in the sample space are equally likely, what we could have done is write down again these definitions. And what we could have done, instead of writing out the intersection, oh, what happened? Oh, no, that's right. That's right. We could have just said the following. Look, what's the union of A and B? We could create a new set that contains all the elements that are in either A or B, or possibly both. And then we could have used the rule we had before. Remember, the probability of V. Now, this is, again, only when each element is equally likely to occur. We could have used that to say, well, you know, that means we could have done the same thing here. In other words, there's 3 elements in the union. There's 4 in the entire sample space, and we're done. But this doesn't always work. Again, this is only true when the elements are equally likely. When they're not, we have to use the addition rule. But it's good to know that you've got 2 options here. All right, so either way, you'll get the same answers. Now, we're going to take a look at an exception to this. First of all, let's remind ourselves, what does it mean for events to be mutually exclusive or disjoint? Well, it means a few things, but it means they have no elements in common. But it also means they cannot both be true at the same time. That means that their intersection is the empty set. So let me just give you a quick example of how this would work. Suppose that A is the set of all odd numbers, and B is the set of all even numbers. Well, do they have any elements in common? They most certainly do not. So since A and B have no elements in common, we can say that their intersection is the empty set. Sorry, I wrote it wrong. And this implies that the probability of this happening is 0. In other words, if I pick, what's the chance that the intersection has an element from both? 0. Now, what does that have to do with the addition rule? Well, if you recall the way the addition rule is written, let me just go grab it again up here. See, there's the full addition rule. If this equals 0, then we can just leave it out. And we have this simpler rule. This is called the simplified addition rule. And so in this special case that the two events, A and B, are mutually exclusive, we can use the simpler version, the so-called simplified addition rule. All right. Now, it may not save us that much time, but it's important to know that this is doable. Okay. So let's see an example of this. Using our same dice rolling experiment, let's try this one. So again, I'll just quickly remind you what's in the sample space. A, the first roll is even, would be these first two elements, E, 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 O. And the B would be this second case, the last two, O, E, and O, O. Now you can clearly see that there's no intersection between them. And so that means if I want to know the probability of A union B, I can use the simplified version of the addition rule, okay? And here we'll note that the probability of A is 1/2 or 2/4. And the probability of B is also the same. The probability of A intersect B, we already know, is equal to 0. All right, so what's the probability of getting either of these two outcomes? So we're going to use the special, simpler version of the addition rule, and it turns out that that probability is 1. Which, remember, we define this as a certain event. It's guaranteed to happen. I mean, it makes sense because if you look at it, A means the first roll is even. B means the first roll is odd. One of those things has to be true. Therefore, this union is called a certain event, and it has a probability of 1. All right, and now, but don't use this rule unless it's appropriate, of course. All right, now, let's look at the second rule is the so-called complement rule. Now, before we do this, we have to explain what a complement is. Now, formally, two events are complements if both of the following things are true. If their union is the entire sample space and their intersection is empty, then A and B are said to be complements. So what exactly does that mean? It sounds cool, the definition is what it is, but let's try to visualize some examples. Let me just throw some at you so you can see what this is all about. So remember, the union is the sample space, the intersection is empty. It has to be both of them. So suppose that a card is chosen from a deck. A is the event that the card is red. B is the event that the card is black. Are A and B complements? Well, we can only find out by looking at these two conditions. Okay, so in this, by the way, in this case, the deck is the sample space. All right, that's an important detail. The deck is the sample space. Whoops, getting sloppy there. Sample space. So is it true that the union of these two events is the entire sample space? Yes. Is it true that their intersection is empty? Yes, because there are no cards that are both red and black. So both of these conditions have been met. So what we can do here is say, in terms of English, the union of A and B is the entire deck, which means the sample space. And that means that all cards must be red or black. The intersection of A and B is empty. And this is because no card can be both red and black. Therefore, A and B are complements. All right, so just think of it this way. All the cards must be either red or black, but none of the cards can be both. All right, so why don't we think of some more examples of complements while we're talking about it? They're not hard to come up with. For example, how about the white and black pieces on a chessboard? The odd and even numbers. The American League teams and the National League teams. In that case, the sample space is all of Major League Baseball. Okay, so you have the white and black pieces. All the pieces must be white or black, but none of them can be both. Odd and even numbers, they obviously don't intersect, but they create all of these so-called whole numbers. And the American and National Leagues form Major League Baseball, but no teams can be in both leagues. All right, now here's, by the way, here's some new notation that we're going to use. Hold on, I'm saving it first. It'll be fine. Hold on a second. There we go. All right. That little c, okay, A with a little c means a complement. And again, don't forget, that implies that the union of these two is the sample space. Their intersection is empty. So with all that being said, there's a rule that we can define for complements, which will make things a little bit easier for us to calculate. So let me show you. There's actually two parts of it. They both mean the same thing. And here you can see them. Basically, the bottom line is that the two of these have to add up to 1. And so that tells us both these two are also true. So if you know the probability of A, you can calculate the probability of A complement and vice versa. Now, in some cases, you can do it directly, like with the playing cards. Sometimes, though, it's easier to use a formula. All right. It's not always the case that you can figure it out directly from the sample space, especially if the sample space is really, really large. That can get very awkward. So instead, we often end up using these rules. And in fact, in some cases that we'll see, we don't even know what the sample space is. The only option we have is to use these rules. All right, well, let's do an example of this. So back to the die rolling experiment. The second roll is even. And the second roll is odd. So the question is, are A and B complements? Okay. Let's prove or disprove it. So first things first, is their union equal to the entire sample space? Yes, you can see it contains all 4 elements. Are they mutually exclusive? Yes, their intersection is empty. So therefore, we say that A and B are complements, and we can calculate each probability from the other. Now, it should be clear that the probability of A is 2 out of 4, and B but we just got through proving that B is a complement. So therefore, we can also claim that the probability of a complement is 1/2. So why don't we confirm that with the the complement rule? And so here we're going to do exactly that. All right. So that one is really simple. So anyway, now the third and final rule that we want to consider here today is the so-called multiplication rule. Now, the multiplication rule is fairly complicated. And in fact, in order to go through it properly, we're going to introduce several new concepts here. We're going to define, in fact, 3 new types of probabilities. What are these 3 new probabilities? They would be conditional probabilities. Then we have unconditional probabilities. And then finally, we have joint probabilities. All of these need to be defined before we can do the multiplication rule. Okay, so we need to go through now. In order to do this, I've created an example in which we have a table, and it's called a joint probability table. And basically, we've got a group of students that are broken up into 2 categories. Okay, so, and again, this will show us the joint and marginal or unconditional probabilities that we need to come up with our multiplication rule. All right, so let me show you the table. Now, this is at a school This is not Purchase. Purchase does not have a business school, but this is the enrollments at a business school. Now it's a fictional school. I just made this up. But in this business school, there are 500 students, and you can see they're categorized by their majors and by what degree they're getting. Now, BBA is shorthand for Bachelor of Business Administration. In other words, this is a business school, and the bachelor's degree that they hand out is called BBA. MBA is the next level up. It's called Master of Business Administration. That's what comes after college. So the BBA means college, MBA means graduate school. So you can see altogether there's 500 people in this business school. Now, suppose I asked you this question. What if I randomly chose somebody from this business school? Oh, before we do that though, I just want to mention that in order to avoid writing so much all the time, we're going to assign letters to these outcomes. Will that B represent getting a bachelor's degree? M is getting an MBA. F is finance major. A is accounting major. Now, unfortunately, marketing, M is already taken, so we'll just use T for marketing. Yeah, it's as good a choice as any. All right, so now that we got these letters straight, we can define some important events. So imagine that I randomly pick one of these students to be on the cover of the alumni magazine. What is the probability that the student that I chose is getting their bachelor's degree in finance? Well, what you would do is you look at the row of bachelor's degree students, the column of MBA finance majors, and you would discover that there's 130 students getting a bachelor's degree in finance. Okay, 130. There are 500 students altogether. So formally, we're going to write this in the following way. Okay, so just a quick reminder, there are 130 students getting a bachelor's degree in finance. The probability of choosing one of these students is 130 out of 500, or 0.26. This is because each student is equally likely to be chosen. So you just count up how many students fall into that category and divide by the grand total, and you've got 26%. And it just so happens that this is an intersection This is what we just demonstrated. At any time, we have a probability of two events both being true like this. This is referred to as a joint probability because two things are both true at the same time. All right, so that is what this table is really all about. It's called a joint probability table because it shows all the different joint probabilities, of course. And we can easily calculate these by just counting how many people fall into each category out of the grand total of 500. All right, so here's another one. The probability that a randomly chosen student is getting their MBA in accounting is 35 out of 500. So let's note that here. Okay, so you can write it as the probability of M and or intersect A. And again, that would be 35 out of 500, or approximately 7%. This is also a joint probability. Okay, so you kind of get the idea. We can do that for any number. Let's see, how many are there? 1, 2, 3. There's altogether 6 joint probabilities in this table. Okay, but there's other probabilities in here as well. Suppose I ask a question like this. What's the probability of getting an MBA? Or the probability that a randomly chosen student is getting an MBA. Okay, so here's what you're going to do. You go back to the table and you say, all right, how many MBA students are there? And let's look at this one. You read across and you say, oh, there's 100. I don't care about their major. I just want to know how many MBA students are there. It's 100. And I know that there's 500 students in the entire MBA business school, rather. So that means that my probability is easy. It's just 100 out of 500, which is 0.20. And now if you notice, this is not a joint probability because only one thing is true. This is known as either an unconditional or marginal probability. Okay, now for these, there's several more that we could do. Let's just pick one more at random. What is the probability that a randomly chosen student is majoring in accounting? We could write that as the probability of A. Now for this one, we go back to the table, and what we're going to do is count up all the accounting majors, regardless of whether they're getting a bachelor's degree or an MBA. Okay, so that means 215 out of 500 is the probability that we're interested in. I just add up all the accounting majors, regardless of their level, and here we are. Wait, now I already forgot what it was. 35, no, 215. This is, and again, this is an unconditional or marginal probability. Okay, so now we kind of get the point there. But there's a third probability, which is more complicated than either of these two, which we'll need to formally define the multiplication rule. Okay, so given how late it's getting, I think maybe we can save that one for tomorrow so that we can go through, we'll review this a little bit. We'll go back and introduce the final probability that we need, which is called a conditional probability. And once that's in place, we can then formally define the multiplication rule. Okay, and when that's all done, pretty much we've got just one more topic in this chapter. So I think we'll be able to at least start chapter 6 tomorrow, which means that you should be able to do, I think I'll post that this afternoon. In addition to the chapter 3 problem set, you should probably also do, let's have you do the chapter 5 problem set for next Monday as well, because again, of course, we have no time. Otherwise, I'd like to give you more time, but we don't have it. So let's, and I'll make an announcement about this. Let's do both chapter 3 and 5 problem set for next Monday, because it's clear that we'll be finished by tomorrow. And then we'll start 6, but that's it. We'll just start it. And then you'll have time to review over the weekend, and you'll have time to finish up the first 2 problem sets, and then we'll take it from there. Now, given how intensely short this semester is, at some point, believe it or not, within the next week or so, we have to start at least thinking about an exam, if you can believe it. Normally during the school year, I usually give 3 exams during the school year. The first one is based on chapters 3 and 5, and then 6 and 7, and then 8, 9, and 10. We'll figure that out, but we don't want to get complacent, even though we just had 2 meetings. Sometime next week, we have to at least start thinking about an exam. But keep in mind, the exam will be a take-home basis. You'll be able to download it and do it at home, and you'll have time to do it. You know, I won't rush you. But yes, so we're zooming along, but that's because we have to. All right. So anyway, unless there's any last minute questions, I think we'll cut it off right here. We'll pick it up tomorrow. We'll wrap up 5. We'll do as much of 6 as we can. And then you can do the 2 problem sets over the weekend. All right. So I guess I'll see you all tomorrow, actually. Okay. All right. You're welcome.